Welcome back to section 2 of chapter 5. In this section, we are going to be looking at properties of quadratic functions in standard form. Last time we were looking more at vertex form, and so we're going to see standard form. We're going to see how to convert from vertex to standard. We won't get from standard to vertex yet, that'll come later. And we'll see how to find different pieces of the quadratic when it's in standard form. We'll see some of them, the vertex and standard, side by side. So our learning targets today: I can define, identify, and graph quadratic functions. Notice we're still graphing. And I can identify and use the maximums and minimums of quadratic functions to solve problems. That maximum or minimum, because the quadratic will have one or the other, is very, very useful and actually solves a lot more problems than one would think. So, we have two forms for quadratic functions. We have vertex form, which is what we saw last time, y equals a times x minus h squared plus k. And we have standard form, which is the y equals ax squared plus bx plus c. This is a form you're probably familiar with from years past. Chances are you remember something called the quadratic formula, which we'll get to in a little while. I'll mention it briefly here, but that uses the equation in standard form. And so we can change from vertex to standard form. And really all this is we're going to square this x minus h, then distribute an a. That's all it is. We're just going to multiply this out. And so the first step is to square the x minus h. Now x minus h squared is not x squared minus h squared, nor is it x squared plus h squared. Don't be that guy. We'll be multiplying these out quite a bit, not necessarily from vertex to standard form, but we'll be squaring binomials. Don't just square both pieces. Don't do it. You have to distribute. It's x minus h times x minus h. And now we can multiply the x and x and h and x, h and h, to get x squared minus 2hx plus h squared. All right, we have x squared minus an hx minus another hx, and then negative h times negative h is plus h squared. Then distribute the a through to get ax squared minus 2ahx plus ah squared plus k. Now our variables here, we have x squared and we have x. And so the a is actually the same. The b is this negative ah, negative 2ah, and the c is this ah squared plus k. So a is just a. The a is the same in both equations. The b, again, was the negative 2ah, and the c is the ah squared plus k. I would not remember this formula to get from here to here. Like these formulas, I would just multiply it out. So if we want to do it with an example where we have actual numbers instead of just letters, first step, we need to multiply out the squared. That'll give us x squared minus 3x minus another 3x, will be minus 6x plus 9. Then we can distribute the 2 through, so 2x squared minus 12x plus 18 minus 1. 18 minus 1 is just going to be plus 17. So we get 2x squared minus 12x plus 17. So try this one. Same basic idea. Y equals 3 times x minus 1 squared plus 2. Go ahead and pause the video, try it, and then when you're ready, push play. How did it go? Did you go x minus 1 squared equals x squared minus 1? Or x squared plus 1? If so, pause the video, do it again, not being that guy. If not, if you went x minus 1 squared is x minus 1 times x minus 1, which gets us x squared minus 2x plus 1. and then you distribute it through the 3 to get 3x squared minus 6x plus 3 plus 2, and then plus 3 plus 2 is just plus 5. Y equals 3x squared minus 6x plus 5. If you did it that way, excellent job. You just transferred it from vertex form to standard form. And so we have properties of these functions. We'll get our two forms up. So we have our vertex form and standard form. And they're both going to have all these properties. They're going to have an axis of symmetry. Now, the axis of symmetry is where the parabola is symmetric. Now, we see it has a vertex, so it comes up, it's symmetric this way, and it's symmetric right around this point, the point of the vertex, the x point of the vertex. In fact, the line of symmetry will be y equals, or x equals this number. But the symmetry part means that we can rotate. It'll actually spin around that. And so we can get our line of symmetry, and then it'll spin around the line of symmetry. And so we see it's x equals this number. Well, what is this number? It's the x part of the vertex. Well, in vertex form, that's just x equals h. In standard form, it's a little bit more complicated than that. It's not just one of the numbers here. It's x equals negative b divided by 2a. Now that might seem annoying and complicated, but really you're just dividing two numbers. It's not that annoying. And you're going to be doing it over and over and over again for most of what we're looking at. And this negative b over 2a, if you remember back to your quadratic formula, it was negative b plus or minus the square root of blah, 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 blah over 2a. It's this negative b over 2a. That's the center. And so the axis of symmetry, x equals h, or x equals negative b over 2a. And notice that's the vertex. So the vertex in vertex form is just h comma k. We saw that last time. In standard form, well, the x part is this negative b over 2a, but what's the y part? When you know the x value, plug it in. We just need to plug it into the function, f of negative b over 2a. It doesn't get nicer than that, but we're just plugging in whatever that number is into the function itself. And then, does it open up or down? As we saw yesterday and in our exploration, that depends on this value being multiplied to the x, this a value. And notice it's the same in both cases. So the rule is actually the same. It opens up if a is positive, and it opens down if a is negative in both situations. The y-intercept, let's start over in standard form for the y-intercept. Y-intercept is when x equals 0. Well, when x equals 0, that's 0, and that's 0. So the y-intercept is just going to be at c. It's going to be the point 0, comma c. Over on vertex form, make x equals 0. That gives us negative h squared, which is h squared times a plus k. It's 0, comma ah squared plus k. It's kind of obnoxious, but that's what it is. And then maximums or minimums. A quadratic will have either a maximum or a minimum. If it opens up, it has a minimum because the vertex is at the bottom. If it opens down, it has a maximum because the vertex is at the top. And the maximum or minimum will be at the vertex. And so here it would just be y equals k. Whether it's a maximum or a minimum, doesn't matter. And over here, it would be y equals whatever this y value is when we plug it in. It's the y value of the vertex. And that is what the maximum or minimum is. Sometimes questions ask, where is the maximum or minimum? If it's asking where is it, that would be looking for the x value. But what is the maximum or minimum? Identify the maximum or minimum would be at the y value. If you are confused as to which one it's asking for, you can always say the maximum or minimum is the y value at x equals blank. In word problems, the context makes it a lot easier to tell which one it's looking for. The domain. Quadratic functions have domain of all real numbers. That doesn't change based on the form. The range. Y is going to be either greater than or less than the maximum or minimum. If it's a minimum, y will be greater than it. If it's a maximum, y will be less than it. And so if it opens up, y will be greater than or equal to the minimum. If it opens down, y will be less than or equal to the maximum. And then same thing over here. Y is greater than or equal to the minimum if it opens up, less than or equal to the minimum if it opens down. Alright, so graphing from standard form. This is going to be very similar from the last lesson. However, we don't have to just plug in x equals -2, -1, 0, 1, 2. We can find the vertex and then use symmetry to help us out. This also helps if the vertex is somewhere other than between those that very short range of numbers. Like if the vertex is x equals 5, plug in those 5 numbers that we used last time wouldn't really help us much. And so that's really the difference. We're going to start with our vertex and then use symmetry to go out from there. And so, but we're still going to make a table. So if we have f(x) equals -2x squared plus 8x plus 5, we have our table. We can put our function in. And now our vertex is going to be -8 over 2 times -2. Is b over 2a. So -8 over 2 times -2. 2 times -2 is -4, so we have -8 over -4, which is 2. And then from here, go up 1 and down 1. So let's plug it in. So 2 squared is 4, 8 times 2 is 16, then 4 times 2 is 8, so -8 plus 16 plus 5 is 13. We can put that in. All right, now go up 1 down. So we have 2 as our vertex. Let's go to 1 and 3. And then 0 and 4. And we can plug these numbers in. We can plug in 1 and 3. And when we do, we'll get the same answer. So 1 squared is 1, times -2 is -2, plus 8, plus 5. Here we'll have 9, -18, plus 24, plus 5. And then, when we simplify, we get 11 in both cases. -2 plus 8 is 6, plus 5 is 11. -18 plus 24 is 6, plus 5 is 11. So we can put the 11s in. Then we can do the same thing with the 0 and the 4. So up here, well, 0 squared, that's 0 plus 0 equals 5. Here, 4 squared 16 times -2, that's -32, plus 32, which is 0, plus 5. And so here we have work shown for all of them. I wouldn't. I'd do it for 2, and then let's see, 1's going to be easier than 3 to plug in, and 0 is definitely easier than 4 to plug in. So I would have found these top 3, and then use symmetry to get the other side of the vertex. And now we can graph it. So we need our big graph, plug in some points, connect the dots in a parabolic manner, and there we have it. So notice it was very similar to what we were doing last time. We just know a starting place. So make a table, use symmetry, try this one. h of x equals 2x minus 1 plus x squared. I would first put it in order. Put it in order for standard form. But go ahead and pause it, graph this one, plot your points, and see what you get. Then push play when you're ready to come back. How do you think you did? Well, let's try this. So we have our table, put our equation in, and then we need a vertex. Well, first let's rearrange the equation. That should be x squared plus 2x minus 1. Now our vertex will be negative 2 over 2 times 1, because negative b over 2a, so that's negative 2 over 2 times 1, which is just negative 2 over 2, which is negative 1. We can plug that in. Negative 1 squared is 1, then minus 2 minus 1 gives us negative 2. Then if we have negative 1, I would go 0 and negative 2, and then 1 and negative 3. In this case, I'd be plugging in these two. Why? Because these two look easier than plugging in these two. So plug in 0. We have 0 plus 2 times 0 minus 1, which is negative 1. If you really want to plug in the negative 2, I have that shown up here, but I would be plugging in 0, which is 0 plus negative 1, which is negative 1, which means negative 2 is also negative 1. Then plug in 1. 1 squared is 1, plus 2 times 1 is 2, minus 1. 1 plus 2 is 3, minus 1 will give us 2. And again, notice up here, we also get 2. Plug that into the table. We can use a graph, put some points on the graph, and then connect the dots in a parabolic manner, and there we have it. Is that what your graph looked like? Did you get these same points? If so, fantastic. If not, see where it is that you went wrong. Right, and then finally, we can use maximums and minimums to solve problems, because a lot of quadratic problems will either be looking for maximums or minimums, or it'll be looking for when it hits the x-axis. But not yet. We haven't gotten to that part yet. So most of these will be just maximums and minimums. Example. The path of a soccer ball is modeled by the function h of x equals negative 0.005x squared plus 0.25x, where h is the height in meters and x is the horizontal distance that the ball travels in meters. What is the maximum height that the ball reaches? So we're looking for the vertex. We're looking for the y part of the vertex, because y is the height. X is the distance it's gone. So first we find the x part of the vertex. It's going to be negative b over 2a. So we have negative 0.25 over 2 times negative 0.005. This will be negative 0.01. Negative 0.25 divided by negative 0.01 is 25. And you can plug that into a calculator if you were really looking for it. This type of question would be one I'd expect a calculator on. So we get x equals 25. That's not the maximum height. That tells us that it reaches the maximum height after it's gone 25 meters. To find the maximum height, we just need to plug this into the equation. H of 25 equals negative 0.005 times 25 squared plus 0.25 times 25. 25 squared is 625, which means that 0.25 times 25 will be 6.25. And then multiply. And then we can add to get h of 25 equals 3.125, which means the maximum height of the ball is 3.125 meters. And it happens at the 25 meter mark if you were looking along the field. And so that's how we can use maximums and minimums. What would be the difference if we were looking for a minimum instead of a maximum? This number right here would be positive. We would do everything else the same. So that would be standard form compared with vertex form. You're going to be graphing again. You're going to be doing a lot of the same stuff that you were doing last time, with a little bit of new stuff, looking for maximums and minimums, and going from vertex form to standard form. A lot of just playing around with equations and graphing. So I'll see you next time, and until then, happy mathing.